Hi students, today our next topic in our first unit wave optics is diffraction. See, diffraction. Do you all know about diffraction? Okay, let us start with the best definition of diffraction. Now, the phenomena of bending of light around the corners of obstacles and spreading of the light wave into geometrical shadow regions of obstacle that placed in a path of light is called diffraction. See here, see here. Here is a light, the waves of light, and AB, that's an obstacle. How the light will split and spread over the obstacle into the geometrical region. See here, this is the screen. So simply the bending of light around the corners of obstacle and spreading of light wave into geometrical shadow region of obstacle placed in a path of light. We are placing an obstacle on the path of a light. So the light can be deviated. That means it can bend and travel towards the screen, and that we are saying that that's the spreading of light. Okay, and next, see the general example for diffraction. The sunlight will reaches the earth through the clouds. How? As a general example for diffraction pattern. Also, for diffraction to be more effective, the size of the obstacle must be comparable with the length of source. See, whenever diffraction is to be more and more effective, we have to compare the size of the obstacle with the source which we are providing for the diffraction pattern. Now, generally, the diffraction phenomena is divided into two types. They are Fresnel's diffraction, Fraunhofer diffraction. We already know about Fresnel diffraction, Fraunhofer diffraction, I think. Now also we can study about Fresnel's diffraction and Fraunhofer diffraction. Let us see what is a Fraunhofer diffraction. See here, this is the Fraunhofer diffraction due to single slit. That means we are having the Fraunhofer diffraction due to single slit, double slit and end slits also. Okay, first start with the Fraunhofer diffraction due to single slit. See this diagram, what you will understood. It's a wavefront, that means a bunch of waves coming from a source. See here, this is a slit, AB is a slit, and having the slit width E, how the light will spread through this obstacle. Here we are placing a lens, and this is the screen. How we can get the P0 and P1, that means here it is a maxima and P1 is a minima. So like that we are getting one maxima and number of minimas. See, consider a slit AB of width E. This is the width, slit AB having width E. Let a plane wavefront W dash of monochromatic light of wavelength lambda propagating normally towards the slit that is incident on it. That means, see, this is the wavefront which we are incident on this slit. So now the diffraction light to the slit is focused by means of convex lens on a screen placed in the focal plane of lenses. See here, we are using lens for the transmission of light to the screen. Next, according to Huygens Fresnel's, every point on the wavefront in the plane of slit is a source of secondary wavelets which spreads out the light in all directions. That means every point on the wave which we are considering, that is in the plane of slit, is a source of secondary wavelets. Those all are the secondary wavelets which spread out the light in all directions. The secondary wavelets is the main reason to spread the light in all directions. So these wavelets traveling normal to the slit. Okay, so that is along the direction of OP0 brought to the focus at P0 by the lens. This P0 is a bright central image. So this is all due to the secondary wavelets, and I already said that P0 is a maxima and P1 is a minima. Okay, now the P0 is a bright central image. Now secondary wavelets traveling at an angle theta with the normal or focus at a point P1. That means secondary wavelets traveling at an angle theta with the normal or focus at a point P1 on the screen depending on a path difference. See here, there is a path difference between the P0 and P1. That is the theta, angle theta. See here, in between every focusing point, that means every line, every wavefront, there is a path difference between the P1 and P0 screen depending on the path difference. Now the point P1 may have maximum or minimum intensity. So to find the intensity at P1, we know that P0, that means P0 is the central maxima, and to find the intensity at P1, there is a minima. Let us draw the normal from C. Normal C from A, the light ray at B. So we have drawn a normal C from A to B. Let us see what will happen. There is a path difference between the wavelets from A and B in the direction theta that is given by. So there is a path difference. We already seen that there is a path difference between the wavelets. That means which are forming the central image. There is a maxima and minima. There is a path difference, and the angle of diffraction. That means angle difference is theta. Now let us see what is the path difference means. From this we are considering a triangle. Okay. Now BC is the path difference. How can we calculate? To know the BC, we have to write sine theta. Now BC equals to AB sine theta. That means BC equals to AB. AB is the slit width. So E, we can write it as E sine theta. Now path difference. We know the path difference. Let us see phase difference. That means phase difference equals to 2 pi by lambda into path difference. This much of integral multiple of path difference, that is equal to phase difference. Now 2 pi by lambda into E sine theta. Let the width of the slit be divided into n equal parts. Width of the slit that can be divided into n equal parts. So the amplitude of the waveform, each part is A. Okay, the actual slit width is E. Now what we are doing here, let the width of the slit be divided into n equal parts. Now the amplitude of the wave from each part is A. So the amplitude also can be divided, that is a A. Now the phase difference between any two successive waves, the phase difference between any two successive waves. We already wrote the phase difference 2 pi by lambda into E sine theta. Now 1 by n. Why we can write it as 1 by n into total phase difference? Because the slit is dividing. That means the slit width is divided into n equal parts, and there is a phase difference, that into total phase difference, that equals to 1 by n into total phase difference becomes 2 pi e sine theta by lambda, that equals to d. Let it be d. And now using the method of vector addition of amplitude, the resultant amplitude R is given by one of the equation of amplitude, and R, here R is the amplitude, and A sine into some x by sine x. That means A sine n d by 2 by sine d by 2. That means here what is d? What is n? N is the slit width. That means slit width is divided into n equal parts, and that equal to a sine n. D must be replaced by 2 pi e sine theta by d pi, sorry, 2 pi e sine theta by lambda. Let it be d. Now the d is replaced by that value, and we already have 2n here. Okay, and now sine r equals to a sine pi e sine theta by lambda. Now this becomes, we are saying this as alpha. Now r equals to a sine alpha by sine alpha by n. Here there is also an n. Okay, and now a equals to a sine alpha by alpha by n. Why? Because for small values sine theta becomes theta. Okay, so like that sine alpha by n becomes alpha by n, because there is a theta is a small, and like that alpha by n is also small. Now na by sine, na into sine alpha by alpha. And next, now small na equals to capital A, we can write it as A. Now r equals to a sine alpha by alpha. We are writing the intensity I, that equals to r square, because amplitude square of the amplitude gives the intensity. So I equals to r square, that equals to a square sine square alpha by alpha square. Now what about principal maxima? We are saying that P naught is a principal maxima. Now see how the resultant amplitude can be written as r equals to a sine alpha by alpha. That becomes a by alpha into sine alpha. For this sine alpha, we can study this as in our intermediate. You just recall that a by alpha into alpha minus alpha cube by 3 factorial plus alpha power 5 by 5 factorial minus alpha power 7 by 7 factorial plus and so on. Now the alpha is multiplied inside, and a equals a into 1 minus alpha square by 3 factorial plus alpha power 4 by 5 factorial minus alpha power 6 by 7 factorial plus and so on. Now I will be the maximum when the value r is maximum. Is it? Now I is directly proportional to r square. So I will be maximum, then automatically r is a maximum. So for this value the negative term must be vanished, that is alpha equal to 0. If it is squared, then it also becomes a positive term. So that's why for this value the negative term must be vanished, that is alpha equals to 0. So we already know alpha equals to pi e sine theta by lambda, that equals to 0. From here we can write it as sine theta equals to 0. So this is the principal maximum. And about a minimum intensity position, let us see what are the minimum intensity positions. That becomes intensity will be minimum when sine alpha equals to 0. Whenever the sine alpha equals to 0. We already said that whenever amplitude becomes 0, then automatically intensity becomes minimum. Like that, whenever the amplitude will be minimum, intensity will also minimum. How or when the intensity will be minimum means when sine alpha equals to 0. That is, whenever sine alpha equals to 0, for alpha values, alpha equals to plus or minus m lambda values. So whenever alpha values are plus or minus m lambda, then only sine alpha equals to 0. When sine alpha equals to 0, the intensity automatically will become minimum. Okay, now pi e sine theta by lambda equals to, we can write the plus or minus m lambda instead of 0. Now e sine theta equals to, it becomes plus or minus m lambda, where m is 1, 2, 3 and so on. Okay, and next, thus we obtain the points of minimum intensity on either side of principal maxima. Yeah, I will show you a diagram. At the center we can get the principal maxima, both sides, on the both sides of maxima we can get the minimus. So we obtain the points of minimum intensity on either side of the principal maxima. And what about secondary maxima? See, in between these minima, we can get secondary maxima. Understood? For a maxima, for a central maxima, either side of maxima, we can get the minimas. Okay? The minimum intensity will obtain on either side of principal maxima. Here, secondary maxima, in between these minima, we get a secondary maxima. Is it? I will show a diagram and you can definitely understand. These positions can be obtained by differentiating the expression of I with respect to alpha and equation to 0. That becomes, we should differentiate the intensity equation with respect to alpha. Now di by d alpha equals to d by d alpha into I value, a square into sine square alpha, that becomes sine alpha whole square by alpha, that equals to 0. Now a square, and this becomes d by d of x square, 2x, 2 sine alpha by alpha, and again sine alpha by alpha is in the form of u by v. So we can write it as, what is the formula for u by v? D by dx of u by v, d by dt of u by v, that becomes, that's the v into du minus u into dv by v square. Okay, so like that, alpha sine alpha becomes cos alpha minus sine alpha into alpha becomes 1 by v square, alpha square equals to 0. And now alpha into cos alpha minus sine alpha equals to 0. Now from here we can write it as alpha equals to tan alpha. Now see how the values will be. The values of a satisfying the above equation are obtained. Satisfying the alpha values, that becomes the values of alpha satisfying the above equation. We can obtain that. We draw a graph y equals to alpha. That becomes, we are known as y equals to alpha and y equals to tan alpha on the same graph. Y equals to alpha ki graph draw chestamu and alage y equals to tan alpha ki graph draw chestamu. The points of the intersection of these two curves gives the value of alpha which satisfy the above equation. See how the graph will be and where it will intersect. This is the y equals to alpha graph. Here a straight line passing through the origin, that's the graph of y equals to alpha, and these graphs are the y equals to tan alpha graphs. How they both will intersect. And now see here at what positions it will intersect. 0. This is, see, that is nearly 3 pi by 2, 5 pi by 2. Is it? So the points of intersection alpha equals to 0 plus or minus 3 pi by 2 plus or minus 5 pi by 2 and so on. Now substituting the above values in intensity equation, we can get that means this is the principal maxima, a square. Now alpha equals to 0. Whenever we are substituting alpha equals to 0 in the intensity equation, it becomes only a square because all the sign values become 0 and sine. And now alpha equals to plus or minus 3 pi by 2. That equals to I1 equals to a square into sine 3 pi by 2 by 3 pi by 2. That nearly equals to a square by 22. Like that, we are substituting again alpha equals to plus or minus 5 pi by 2. Again we are getting some value. That means this is the first secondary maxima and this is the second secondary maxima. That becomes, in between every two minimas we can get a maxima. Okay, we can get a secondary maxima. That becomes, let us assume these two are the minimas. Okay, in between two minimas we can obtain a maxima. Okay, is it? So simply this is the intensity distribution according to Fraunhofer diffraction due to single slit. Okay.